Okay.
Okay, so thank you all for coming, particularly at this unconventional time for a colloquium. Now we are going to have an extraordinary colloquium by Ryan Foley, who's here also visiting with Shri, who was giving a talk yesterday. So I am going to introduce him. Dr. Foley holds a bachelor's degree in physics, mathematics, and astronomy from the University of Michigan, a master's degree and a PhD in astrophysics from the University of California, Berkeley, and he has been a Clay Fellow at Harvard-Smithsonian Center for Astrophysics and an assistant professor at the University of Illinois at Urbana-Champaign and at the University of California, Santa Cruz, where is his current position. He is a leading observational astronomer specializing in the study of supernovae, gravitational waves, and dark energy. He is widely recognized for leading the team that discovered the first optical counterpart for a gravitational wave source, which was a binary neutron star merger. His research focuses on using cosmic explosions to measure the expansion of the universe and understand the physics of stellar death. And today, I think he's going to talk about the Young supernova experiment. So, thank you.
I'll take what I can get. Okay. All right. I think I'm going to stay down here with the people. This is a slide here that I show to prospective graduate students to kind of talk about everything that me and my team, and really when I say me and my team, it's my team, that are working on a bunch of different areas of research. I am primarily going to talk about, of all these projects, this one here, the Young Supernova Experiment, which uses about 8% of the 2 Pan-STARRS telescopes and about 17.5 nights per year of the CTIO 4-meter with DECAM. But before I dig into that, I was very inspired by a lot of moments in this trip, including the other day we had this really exceptional tour, and from as we walked over to the pyramid of the moon, and then at at that platform looking out, I mean it's a marvel of the world, right? Like, this is one of the most impressive things that I've seen, and it's very inspiring. And so that, combined with all the discussions that I've had with everybody here, which have been fantastic. Thank you so much for having us here. And then Shree's talk as well. I decided to kind of just say first, I hope these discussions can continue on, that you can visit us in Santa Cruz. This, it's here. We have the ocean, we have the trees, we have a boardwalk with a roller coaster, sea otters, banana slugs. The Santa Cruz mascot is a banana slug. And this is also where surfing started on mainland North America. And that's where the wetsuit was invented. It's where mountain biking was invented. It's really a fantastic natural place. And we also have some great scientists. This is Sandy Faber, when she was getting the National Medal of Science, good, from a president that we actually respected and looked up to. And so, yes, I hope you can come. And part of that is that we at UC Santa Cruz, we have a very special place within our community. We are a public university, which in the United States, there are a number of public universities, also a number of private universities. And the missions of these different universities are often very different. And the mission of the University of California is to educate the population of California. And I think the University of California is the best idea that the United States has ever had in terms of economic development, in terms of science. It's just been fantastic. Ideas, you can trace so many things back to the University of California. And Santa Cruz in particular, it's a relatively young campus, but we are the headquarters of the University of California Observatories, which runs the Lick Observatory just east of us near San Jose, and then also is one of the members of the Keck Observatory and TMT, the 30-meter telescope. So we in particular have a lot of connections within astronomy at the University of California, Santa Cruz, and there's a very large astronomy community there. We're a Hispanic serving institution, which in the United States is an official designation, where roughly a quarter to a third of the students at UC Santa Cruz are Hispanic. And about 15% of the astronomy PhDs are either Mexican or Mexican American. So we really have this shared history between California and Mexico, which at times might have been troubled, but I think now we can look at California and say it could not have been built without Mexican Americans and previously without Mexicans. And we continue to grow from Mexicans coming to California and from the Mexican Americans that grew up there. So if I can just say, the United States right now has a lot of problems, but California is a little bit different. We are not the average spot in America. And I think part of this has really been shown in the recent protests related to ICE, this immigration and customs enforcement, and all the truly terrible things that they've been doing. And so you will often see at these protests a Mexican flag showing that strong support for the Mexican community within California. And so I understand that maybe some people would be a little hesitant to come to the United States right now, but I just want you to know that at Santa Cruz, you are very much welcome. So with that, I wanted to ask a question, and this is really designed for the students, but I hope that the professors also think about this. So what is creativity? I'm curious, anybody, but especially a student, do you have an example, an idea, a definition of what creativity is? Okay, go ahead. Oh, and with the microphone, good.
An idea I have about that is like maybe using the building block that you have, like maybe ideas or something else, to try to create or design something that's new based on something that already exists, to try to innovate in some way. That's like, well, an idea.
That's fantastic. So looking at a problem from a different perspective, that's a great way to be creative. Essentially, creativity is that synthesis of various knowledge and other ideas to attack one of these problems. And so for the longest time, I both thought that I was a relatively creative person. I could come up with ideas. But I also thought that was an innate quality that you could not learn. I've been thinking a lot about this recently. And what I can say is that you can learn to be more creative. And we should focus on this as part of our training as scientists. So how can we learn to be more creative? Now that I've told you you actually can learn, does anybody know how you can be more creative? I'll even look at the front row of all the professors.
Give yourself time to think.
Oh, okay, interesting. So Enrico said to just give yourself time to think, which is a very, very much like how I used to think, no offense, Enrico, of just like, oh, it's an innate quality, it will bubble up to the top.
No, just allow you time. Don't try to find a quick solution to all the problems.
Okay, all right, so give yourself the time to think.
And doubt everything.
Sorry?
Doubt everything.
Adopt everything.
Doubt.
Oh, doubt everything, to be skeptical. Okay,
Not skeptical, but not to take everything as a
okay.
result and you don't have any.
Okay, yeah, we can try one more. This is the important thing.
Hi, me again.
Yes?
Yeah, for example, I could think that maybe we are now like scientists, but maybe try something different, like a language, arts, or something like that, and then
Perfect.
try to apply that to science.
Yes, perfect. That's actually how I have come around to think of creativity, is that when you are actually able to come up with a creative idea, something that nobody else has ever done before, it very rarely is the thing right in front of you. It is almost always because you were able to look at that problem from a different direction. And so I will use an astronomical example here. Does anybody know what this is? All right, somebody just yell it out.
Radial velocity curve.
For what? This is a radial velocity curve. For what in particular? Does anybody know? This is famous. Sorry? Wait, I can't hear. I can't hear. The first exoplanet. This is 51 Peg B. This is the first exoplanet. And if you don't know the story behind this, this radial velocity curve should not have happened, apparently, because the size from peak to trough, that amplitude, is much higher than what you would get from Jupiter. And so this particular radial velocity curve and some other work led to the recent Nobel Prize for these two authors. Now, anybody know what this is? I don't expect you to, but this is 70 Ver B. This was the first radial velocity curve that was published by a group at University of California, Berkeley. And they had figured out something from that first 51 Peg B discovery and decided to look at their data a little bit more. And the reason is that first planet was a hot Jupiter. It had an orbit that was much shorter than Jupiter's orbit of 12 years. People weren't expecting that because they thought every exoplanet would be in a solar system like ours. So if you look at the data, this is the data for that 70 Ver B. If you look at the data, you can see they were getting data for this exoplanet for years. And then after the publication of that 51 Peg B, they started getting a bunch of data here. And then when you fold the light curve, you get this great phase curve. But you could have done that years earlier. Why didn't they figure it out? Well, they weren't expecting to have this level of amplitude. And so they were saying for all those years, one, they needed to improve their measurements so that they could detect Jupiters around other stars. And two, they just they didn't look at any of the data because they had no expectation that they would see any planets until after a decade. That was a lack of creativity. And this happens all over in astronomy. The fact that you can, if I can go back, the fact that you can see this curve here and look at it and you say, this is a 50 sigma result, something like that. The first exoplanet is some giant sigma result. It's not 3 sigma, 5 sigma. that tells you that people just weren't thinking about it in the right way. Okay, so with that, I'll just say that, maybe before I dig in, that you all have the capability to be incredibly creative. And, I really do believe if you are somebody who enjoys the arts, science, if you travel in particular, these are ways that you can see the world from different viewpoints, get different perspectives. You're able to then attack these problems in a lot of different ways and be more creative. And okay, so, I've been very lucky. I've been able to meet people all around the world. I bring some of that in with me. But the best way to really be creative is to get a bunch of people with different life histories, different perspectives together to solve a problem. And so what I can say is that my history is different from all of yours. What I bring to the table is different from what you do. That my solutions will not necessarily be your solutions, and that your creativity, your unique way of looking at the world can beat anybody, can make it so that you have that great idea today. So don't hold back. Okay, so Shri mentioned this yesterday. I will point out some of the language from the US Decadal Survey about transients. And you can read it on your own, but I think the main thing is just that time domain observations are a central element to our top ground and space-based projects, and they offer tremendous new discovery space. This is the decade for time domain science transients. And we have recently been able to just dramatically change the way we can study these objects. And I think, a reasonable person sitting in the audience to say, okay, time domain, why does that matter? Well, what I can say is that whatever you study, it probably connects to exploding stars in one way or another. They're essential for, providing feedback in galaxies. These sorts of things create gravitational waves. You have cosmic rays. Of course, they're connected to stellar evolution, cosmology even. So essentially everything is somehow related to exploding stars. So not only should you be listening, even if you work on, for instance, the nuclear equation of state, even then, you should be thinking, all right, transients are clearly connected to my science. But also, I'll just say that intrinsically, they are incredibly interesting. And why this is such a fun topic for everybody is that they are some of the most energetic events in the universe. And so, for instance, at the end of a massive star's life, you have this onion-like structure, where at the center you end up getting an iron core. And for the students, ask your advisors why it's an iron core and not a nickel core. I bet some of them don't know. And so with this, eventually you end up undergoing a supernova explosion. And this very, very tiny iron core, which is embedded inside of all these other layers, when it collapses down to a neutron star, that gravitational energy that's released is able to eject all of this outer material as a supernova. And so when we're thinking about studying those objects, trying to understand how they explode, what stars actually do explode, which stars might directly become a black hole, we need to go out and look. And Shri really talked about a lot of the history of supernova searches in the past. And I just wanted to show how dramatically different things have been recently. This is the number of supernovae that have been discovered over time. And if you were to look at this as you all are right now, you'd probably be like, oh, we didn't start finding anything until about 2000. Well, all right, so this is a linear scale. Let's switch to a logarithmic scale. There has been this orders of magnitude increase over the last couple of decades. This is really changing, where in the past, this is sort of like foraging for supernovae. There were a lot of times you'd just take a picture of a galaxy and be like, oh, that looks different. And you'd find a supernova in the same way that you kind of like find some berries or something walking around. Then there are also these hunting, where you go out systematically looking for supernovae, usually targeting big galaxies because that's where the stars are. Recently, with surveys like ZTF, you have this gathering situation where you can go out at the sky and you can say, all right, I really, I'm going to want a bunch of supernovae every night. But very soon, we're going to move into this agrarian lifestyle, where essentially you can order up whatever transient you want on any given night.
I thought you are producing.
Yes. I actually, sometimes I call this the fast food, but yes. And this is all driven by LSST, the Rubin telescope. Okay, so what I'll say though is that having 1 million supernovae, that doesn't necessarily tell you much in science. And so say you want to look at the very youngest supernovae, things that happen only a few days from explosion. Even the very brightest supernovae, things that are like the brightest supernova for the year, you're maybe going to find them about 10 magnitudes below peak, which corresponds, for this sort of increase in brightness, maybe a day after explosion. Now, if you're looking every 5 days, okay, you're going to miss a whole lot. But because this is rising so quickly, if you observe every night, then you only have to go 5 magnitudes below. It has risen 5 magnitudes in 1 day. And so cadence really matters rather than depth for finding things that are, say, very young. These are the sorts of things that maybe, LSST is just not going to deliver, but if you're creative and you're able to do something interesting here and have a cadence that's pretty short, you might find some very interesting objects. Now, you have to be careful because you don't just want to find a bunch of young objects. You want to be able to identify them as young. And so if, for instance, you took 2 images that were maybe an hour apart, all right, the supernova has gotten a little bit brighter, but the uncertainties in your measurements might not be sufficient to say, oh, there's a 3 sigma brightening. And so what you really need to do is figure out what kind of cadence you should have to maximize this. And it's very difficult for an individual survey to do this well. So Assassin is a very nice survey that is pretty much all sky. They have northern and southern telescopes. Atlas as well, northern and southern telescopes. ZTF has been fantastic at finding a whole bunch of supernovae. And all of these data are public. But I can tell you that when somebody from Atlas is looking for a supernova, they're not looking at the ZTF data. Why? It's public. Okay, so years ago, I came up with this idea to say, all right, we have all this public data. How can we leverage it? Right, this is where you have to say, all right, everybody has access to the data. How can you have that good idea that makes you stand apart? And so our idea was to use many telescopes around the world, combined with all these public surveys, to really be able to image the same parts of the sky several times a night. And this is a large collaboration, international collaboration. UC Santa Cruz leads the project, but really there are so many people who have contributed to this. This is one of the telescopes we use. That's one of the Pan-STARRS telescopes. There are 2 Pan-STARRS telescopes. They are really made for transient science. So the idea is something like this. So we have a bunch of time with DECAM, that's in Chile. Our images typically have a limiting magnitude of about 22.5. That's pretty deep. All right, so we take an observation with DECAM. All right, then you say, all right, pan-stars, that goes a little bit shallower, but still relatively deep. Because the Earth is rotating and Hawaii is at a different longitude, that means that you naturally have a 6-hour gap. Then you wait for the Earth to rotate some more, and then ZTF can observe it, 27 hours after DECAM. And then you can, again, hit something like Atlas, which is even shallower, 30 hours after. That's the basic idea, but we use more telescopes than that. And so if you look at the Earth here, all right, this is a relatively recent image of the Earth. All right, so say you have your DECAM, you have ZTF. All right, you move forward in time, other telescopes like there's a telescope in New Zealand called MOA. One of the Atlas telescopes is in South Africa. As you move around, essentially at all times, there is a telescope that can look at the sky. So, this is why sometimes we say the sun never rises on the young supernova experiment, because we kind of are always in the dark. Okay, so what that means is we can find supernovae early on and have this incredibly dense photometric light curve early on. And then later, when things are older, we don't need to have the same density. So we'll get back to this supernova in a little bit. This is a particularly interesting one where that high density of data early on was very important. So we've already put out one data release, so anybody here can download the data, play around with it. It's about 2,000 transients spread out kind of over the sky. And for those, we also have included the ZTF data. And like I said, some of the separations in time between, say, ZTF and pan-stars, that is pushing things out to these time scales like 3 to 5 hours, or around 19 hours, or around 28 hours, that you don't get from one of those telescopes alone. Now, we are currently working on getting our second data release out, which will include a lot of those other telescopes, including especially DECAM, which will also fill in a lot of these gaps. And so our first data release has about 2,000 transients, and about 500 were spectroscopically confirmed. There are about 1,000 type 1a supernovae. This is an incredibly precise millimag precision photometry for those type 1a supernovae. And our second data release is going to be at least 10,000 transients with 4-band photometry, GRIZ. Over 1,200 will be spectroscopically confirmed, about 9,000 photometrically classified. So several thousand 1A, several thousand type 2 supernovae, these core collapse supernovae. It's significant. But, the spectroscopic confirmation is very useful. And so one of the things that we can do, for instance, is ZTF has this bright transient survey that's been very complete, like 93% complete down to a relatively reasonable brightness. And we can just say, all right, for those same objects that we have data, you can look at all of those. And this is, whenever I made this plot, about 500 supernovae that have all of the GR light curves from ZTF and GRIZ light curves from the young supernova experiment. And those extra bands are particularly interesting because that maps better to what LSST is going to do, because it has those bands. And so, for instance, if you wanted to have a photometric classifier and train your photometric classifier on a data set, this sort of training sample will do so much better at predicting what LSST will be able to do. Part of that is also, we go deeper. So there's a lot that can be done here. But one of the things that we've been pretty good at is by having those extra bands, you can separate out the young supernovae from the old ones from a single night. Just if you have this sort of color diagram, this was one of our first type 1a supernovae that was discovered about 2 days after explosion. And you can see that it matches up with what we thought for type 1a supernovae. Here is the 2 days before explosion. So if you only had the G minus R color, it's harder to distinguish. And with reddening, it gets even harder. Okay, so I showed this video before of 20 OI. This is a very interesting supernova. It's a type 1c supernova. That means that it comes from a massive star that has lost its hydrogen and helium envelopes. And so these are relatively rare. And what was very interesting about this is that because we were able to get high cadence observations early on, we were able to figure out that there was this evidence of a shock breakout, that all at once, the light that was coming out from this explosion hit a surface where things went from optically thick to optically thin, and that light just came out all at once. And then, later on, it continued to evolve. So when we tried to model this, one of the interesting things is that there is a data point from roughly a day before we started getting this high cadence data. And you shouldn't expect from a compact star, like something that is lacking its hydrogen and helium envelope, to have a shock breakout that lasts days. It should really be minutes. And so we think that what it is that there was some sort of circumstellar medium, likely asymmetric, where you see that first data point from material that happened to be close to the star, and then the rest of this light curve from material that was a little bit further away. Now, for the binary star experts, you can say, oh, this circumstellar medium that happens to be very eccentric, that's interesting. Okay. Now, this behavior of looking for things as the stars are very young has led us to a bunch of interesting activity that we could not have predicted. So for instance here, this is a star that was slowly brightening for months, years, and then at some point as it gained in brightness by a factor of 100 or more, then we think it exploded. This particular object is very interesting, and we have data because the Young Supernova Experiment uses the Pan-STARRS telescopes. We have data going back about 15 years before that to the start of the Pan-STARRS surveys. And so we can track this all the way up through explosion. And if you zoom in on the early time evolution of this for years, and all right, so it's very noisy here. Let's remove the noisy data and just stick to the DECAM and Pan-STARRS data. And you can clearly see each one of these little groups is a season where you were able to observe it, and then it goes behind the sun. So this is 1 year, another year, another year, another year, and you can keep counting years back. So not only has it been rising for several years, we also think that there's variability for even years earlier. Now, this is such an interesting event because it happens to be in a very nearby galaxy that has a whole bunch of archival imaging from Hubble and JWST. So we can look at the star, and we know that this is the star that exploded. And if you say, all right, what's the luminosity of that star? What's its temperature? You can put it on an HR diagram. And its progenitor is up here, brighter than any star in our Milky Way. So, how do you want to extrapolate the mass here? I don't know. But, it probably was over 200 solar masses. Okay, so that's fantastic. This also happens to have been imaged with JWST before it exploded. This is the first time that JWST has seen a supernova progenitor star. So in this little area, you can see here, this is before explosion, only by a few weeks. And then this is JWST data that we got almost a year after explosion, and that star is much brighter. Now, these are bands at 5.6 microns, 18 microns, 21 microns. Now, for people who understand black bodies for stars, you shouldn't be seeing something that is super bright here if it's just a star. Instead, we know that this is a very dusty source. And the pre-explosion SED is here in orange. And then the post-explosion SED, including this incredible JWST spectrum, is here in purple. And so this in particular, this is a dust feature related to silicate dust grains, which maybe there's some evidence of that from the pre-explosion photometry as well. So this is the first time we really have the opportunity to precisely measure the amount of dust before explosion and the amount of dust after explosion. And we can ask the question, how much dust is formed in this explosion versus how much is destroyed? This is one of the fundamental questions of how the universe was so dusty at early times in the universe. You look at a redshift 6 quasar, there's already a whole bunch of dust around that quasar. Where did it come from? And so this might be one of the possibilities if it continues to grow more and more dust as we go along. Because we think so far, this is primarily just the pre-explosion dust that just hasn't been destroyed. Okay, now, similar idea, but for a normal type 2 supernova. So this supernova has its hydrogen envelope. Came from something like a 10 solar mass star. And there is a question.
Yes, before you continue, because I'm curious, you say that you can measure how much dust is in the galaxy. How do you know that this is real? Okay, this is for the environment of the star, but is this something that you can extrapolate to the galaxies in which we know that are these explosions?
Yeah, so good question. The real not paradox, but the big question is, how do you form so much dust early in the universe? Most of the dust in the Milky Way is being formed by AGB stars. If you go to redshift 6, AGB stars don't exist. There hasn't been enough time for them to evolve. Now, we know also that you can form dust in supernovae, but a question has been for a very long time if those supernovae can produce enough dust early enough. And even more importantly, are they net producers of dust or net destroyers of dust? Because if there's dust near the star and then the shock wave runs through that, you're going to destroy that dust. So you have to say, all right, I'm going to destroy that dust. In the ejecta, can I form enough to make up for that destruction? And can you do that in that very short amount of time between the first stars and when we see all that dust in these high redshift quasars? That's the hard part. And so this is a whole lot of dust compared to other supernovae. And a good question is, because we think, although not great data, is that dust growth kind of goes like this. You start off very low, and then you start to grow over time. Well, if you start up high, do you continue to stay high? Or do you just sort of move over to here and then start growing further? We don't know yet, but we're continuing to get JWST data for this one to answer that question. Was that okay? All right, and Danny.
You saw the dust, but why would it form back later? It's done already?
The dust forms in the ejecta. So the shock wave will destroy dust that is exterior to the system. Oh, so in that material, when you're sweeping it up in the shock, you might be able to reform some dust, but you are at the same time dispersing that material. Yes, yeah. So these are things that people have thought about now for decades, and we're finally getting some data. So yeah, you're right to question all of it. Okay, so say you have a 10 solar mass star, it explodes, a normal 10 solar mass star. You see this very interesting behavior where the supernova gets brighter right away, and then it's relatively same brightness for about 100 days. That's because of hydrogen recombination. And this we see all the time. These are very common supernovae. But this particular supernova was very interesting because with the young supernova experiment, we could go back in time, and very early on, we saw that a few months before the star exploded, it got a little bit brighter. So this star, a normal 10 solar mass star that creates a normal supernova, it just increased in brightness by a factor of a few months before it explodes. Now, that is maybe not crazy, because in the last few years, months, even days before a star explodes, you're rapidly going through nucleosynthetic layers where you're starting oxygen burning, around here. You have silicon burning beginning really, sometimes depending, the most massive stars days before. And so our supernova, the star, started to get brighter a few months before, coming out here. And you can see that all of this starting of the oxygen burning around here, silicon burning around here, there is an expectation that the overall energy is going to be increasing in the core. Now, how do you diffuse that energy out to the surface? Still not clear. But at least there's a mechanism here, and that means that maybe we can understand the last stages of stellar evolution by looking at supernovae and then going back. But to do that, you need to, in this beautiful movie of, although it's flagging on Zoom, of what we think happened. All right, somehow it got a little bit brighter. Okay. And then, all right, then it explodes. Good. Okay. So if you find a supernova like this, you can go backwards in time and see if there was any rise in its brightness. There have been extreme events where we think these are LBVs, they have some sort of outburst, or shells are running into shells. That sort of stuff we've seen in a number of different surveys. And those are the sorts of things where if you have a survey like ZTF out to 100 megaparsecs, you can see. If you have a survey like the Young Supernova Experiment, we go deeper, you can go a little bit further. If you take this same supernova, though, it was relatively nearby, about 40 megaparsecs. You put that at 100 megaparsecs, Young Supernova Experiment will not be able to see that at 100 megaparsecs. But LSST will. The number of type 2 supernovae within 100 megaparsecs is very large, dozens, every year. So we can check this and see if this is normal behavior, if it's somehow related to the progenitor star, somehow related to the explosion. This is something that we will be able to do very, very soon. Okay. Now, Sri, despite showing many, many examples of how his anomaly detection system, that is his eye, created this full phase space of transients, said that anomaly detection with current surveys is maybe not the most productive thing. But I think there's actually a whole lot here that we can do if we are physics motivated. And so, for instance, as part of the young supernova experiment, we were following this event, and it was rising very slowly. And then at some point, this algorithm, this AI algorithm that we have to determine if something is normal or anomalous, it flipped over on this date. This is the overall score that we had. So above 0.5 means that it's anomalous. On that date, it was 0.54. And you can see the individual features and how much they contribute to it being anomalous or normal. But the point is that we flagged it here, and then the supernova continued to evolve and then re-brighten it. We didn't know it was going to do that when we flagged this. But because it was flagged here, we were able to get more data, get spectra. And so this is the real value of anomaly detection. Because, if I were looking at this by eye, maybe I would think that it's a little bit odd, maybe not. The point is to automate it so that you don't have to worry about this. The computer will tell you that, hey, this is interesting, and then you can get data. So that particular supernova, the first author came up with a scheme which works. Maybe it's a little contrived. So the idea is that you have a massive star that is in a binary orbit with a black hole, both about 10 solar masses, and they merge. So you had some material ejected early on, they merge. After they merge, very shortly after they merge, there will be an explosion, and then that explosion is interacting with this other material that was ejected earlier. Again, it's pretty contrived, but it does match the data. And so you might imagine it looking something like this. Okay, so I just wanted to state that for us in the Young Supernova experiment, we are very, very junior scientist focused. Every single paper that has come out of our collaboration has been led by either a student or a postdoc, every single one. That has been one of our primary goals, is to continue that. We have had over 150 students and postdocs involved at one point or another. And UC Santa Cruz has involved, dozens of people. So I think in addition to the science that we can do, this has been an incredible resource for networking for junior scientists. And the students who have graduated as part of this program have done extremely well. So, all right, let's move on to LSST. LSST is going to provide a lot of light curves, something like GRIZY, for million supernovae, something like that. But like I said, this alone is not enough. You need to somehow look at the data, find the interesting objects that you want to follow up. Well, so the same basic anomaly detection, on the day that Ruben first started putting out public alerts, which was around here, we flagged this as anomalous because it has all this data going back several months that they just didn't make public until that day. Why? Well, it's rising over several months, which is pretty unusual, not impossible, but unusual. And then there's this little precursor brightening and fading. And so we got a spectrum of this with the Gemini telescope and found that this is a superluminous supernova at a redshift of about 1. This is the first superluminous supernova from Ruben. And so once you have that redshift, you can place all of this in context, and you can see that at peak, this was about minus 22.7 magnitudes. That is, about 3.5 magnitudes more luminous than a type 1a supernova. Okay, so how are we going to keep up with these millions of alerts that are occurring every night? My very small solution is to use this telescope here This is the APF telescope at Lick Observatory, which again, University of California Observatory at UC Santa Cruz runs this observatory. And this is a particularly interesting telescope because it's 2.4 meters, pretty large, and fully robotic. Currently, this telescope only has a high-resolution spectrograph. The name of this telescope is APF, the Automatic Planet Finder. So it just has a high-resolution spectrograph. But I am building a dual-beam, low-resolution spectrograph for this. And so we will be able to switch. Both instruments are at Naismith. Just switch the M3 mirror and be able to use both at any time during the night. And so the idea right now, this is sort of our workflow. LSST produces all these alerts. There's somebody from my team who looks through the alerts. They say, oh, this is interesting, tells maybe another person, hey, this is interesting. That person then calls up their friend who's at a telescope. Can you get a spectrum? Somebody gets a spectrum. Then somebody has to reduce the data. You get a spectrum here, and you say, oh, that's a type 1a supernova. And then you have to send out some alert to the community. And this whole process can take 36 hours. And when you're talking about the sorts of things that I've presented, where you want to look at things within a day of explosion, 36 hours is killing you. But we live in a magical age where we plan to have this workflow, where there's an AI process to select the targets and immediately put them into the queue for this telescope, which has this instrument. There will be a data reduction pipeline that is automatic and automatically classifies the spectrum, and then automatically set out to the community. And that can be done in under 5 minutes, with the exception of how long you expose. So this is the idea. This spectrograph is going to have first light in about a year. Pretty well timed to LSST. And since this will be the largest robotics low-resolution spectrograph, this is a unique position for time domain astronomy. So I'm looking forward to that, and I'm always looking for smart minds who are willing to help make these algorithms. I'll point out that each one of these images I made with AI. I said make a graph of like having transient alerts and turning that into something for a telescope. And you can see, I don't know, there's a little spaceship or something. Okay, all right, anyway. With that, I'll end and just say, really, the future is bright for time domain astronomy. And I don't want everybody to just immediately jump on board, but I think a good fraction of you, especially people who still have very much your life in front of you, opportunity to take advantage of this. You should really be thinking about what you can do with these amazing new resources that are coming online. The ability to collaborate with people who really want to bring in new ideas, new perspectives. And so I really just, from the bottom of my heart, thank you all for just being so welcoming and all of the great conversations that I've had so far. I'm looking forward so much to meeting with the students. And if you have any questions or you want to send me any kind of information, here's my email address. Thank you all very much. No idea.
Thank you. So we have lots of time for questions.
So the
Oh, yes.
the supernova where you had the pre-explosion imaging with JWST, was that just good luck, or how did you know to take the image of JWST beforehand?
Yeah, so good. So the question was for was this the JWST one or yeah, okay. Yeah, so JWST, we got lucky that it happened to be in this galaxy that's very nearby and happens to have an AGN. It's actually the closest Seyfert 2. And so people have just hammered that galaxy. And so, yeah, we got lucky in that sense. The The place where maybe there was a little bit more than luck is that the data were originally proprietary at that time, and we reached out to the group that had the data and made an arrangement. They shared it with us. Then it happened that there was another group that also wanted to look at the AGN, and they looked at it for that late time image. All right, we made another agreement with that group. Those are the sorts of things where if you know it exists, then yeah, try to figure it out. And then we also put in our own proposals, like that spectrum came from us. So this happens fairly regularly now, where there's some sort of pre-imaging. Roughly a third of the supernovae within about 25 megaparsecs have some sort of pre-explosion space-based imaging. Yeah. Well, that was the first one. There's been a second one now, but that was the first one. So one of the JWST big programs from the first cycle was looking at these nearby galaxies, and so that helped. And Enrico also wanted me to talk about some of the non-transient science with the young supernova experiment. And I'll just sort of give you an idea about this. We've imaged roughly 1,500 square degrees of like the lowest extinction high galactic latitude sky. And we now, in our stack depth goes to something like 25, 26 for that. That is roughly 3/4 the area of dark energy survey, but about 1.5 magnitudes deeper. So the volume that we have is significantly larger than the dark energy survey. And essentially nobody has looked at the static sky data. So that's something where if somebody was just like, hey, I want to do this, there's my email.
Galaxies.
Yeah, galaxies are going to be fantastic. Stars even. If you want to look at R. Lyrae in the halo, oh my God, we would go out 50 kiloparsecs. Okay.
Thank you for your talk. I want to ask the question of questions. I probably know the answer because if you have detected the progenitor of supernova type 1a, you would be talking about that non-stop. So what's the prospects of doing that?
Okay, good. So type 1a supernovae, we know they come from binary systems where one of the stars is a white dwarf, a carbon-oxygen white dwarf. The other star, not so sure. So if you could directly image that system, that would be really interesting. And so for normal type 1a supernovae, this has not happened. And sometimes we have had pre-explosion imaging that's particularly deep, and the non-detections are really pushing us for at least those systems being two white dwarfs. Now, that said, there's a very interesting class of supernovae that are related to type 1a supernovae called type 1ax. Near and dear to my heart. I've studied them a lot. And one of the great things that I was able to do in the kind of decade that I was really pushing on that class of supernovae was find a progenitor system for that particular one of the supernovae in that class. It's a thermonuclear explosion, so there's a carbon-oxygen white dwarf, but the other star seems to be a non-degenerate helium star. And that is mind-blowing. In fact, for that class of supernovae, we've essentially figured out the progenitor problem and everything else. It's very interesting. The white dwarf is not completely disrupted, at least some of the time. It's very interesting. We know more about that than the normal type 1As.
It is very interesting.
Yeah. Yeah, okay, good.
Okay, so since you can see all this, I guess you can also see low mass X-ray binaries in the galaxy when they are creating easily. No?
Yes, yeah.
And there's something fascinating that the transient low mass X-ray binary, I'm not interested in supernova, but X-ray bursts and stuff like this.
Yeah.
And because most observation X-ray bursts are when the star have been accreting for a long time, but it's a very interesting when it's in quiescent for years.
Yes.
And then suddenly accretion start. When does the X-ray burst would start? Mm-hmm.
Yes.
And it's funny, something I always say in the textbook that you have a hydrogen-triggered X-ray burst was described in the 80s. The first observed hydrogen X-ray burst was observed recently. For 50 years, people talk about this and never see anyone, no?
Yeah.
Because it happened at the very beginning, the first few hours during the accretion, it starts,
Yes.
no?
Yes.
So it would be great to be able to look at all these X-ray binaries. They're known, okay? But one of them is seen in optical, immediately look at it with Swift
Yes.
and see the first burst. Because there are a lot of physics you can learn from this. No?
I agree. We should do that. With pan-stars, we have this time series data going back 17 years. So yeah, there's a lot of potential there. Oh yeah, you know, so right. So with the young supernova experiment, we are lucky that we are able to do what we want with the telescope. And so we have in the past imaged some globular clusters. We could do that again. We do a nightly cadence on the Virgo cluster because, you know, the supernovae that happened there are very interesting. Of course, within the Virgo cluster, there are all sorts of other variable stars that are also very nice. So there's a lot that we can do. Yeah. Yes. 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 So yes, and we can do that.
And you know what they are. You don't have to
Yes.
find them. We know.
Yes. Yes. Good.
More questions. Is there any
Yeah,
question in,
Especially from the students, if
in Zoom? No?
Well, first of all, thanks for the talk. And I think it's very interesting, but I hate to be this person, but I think it's necessary. From what I know, whenever one's sort of planning to build a new telescope, a new site, during the siting process, there's a need to check the environmental impact, maybe in the fauna. So I do get why it's necessary to reduce those 36 hours to 5 minutes, I think it was. And I get that it's AI that's going to help us get there.
Oh.
What I don't know if you've checked the environmental impact due to the
Of
water
using
use.
AI.
And, yeah,
Okay, all right. So
yeah.
I think we're all starting to figure out exactly what's happening. Let me first set the facts down, which is using AI in this way, essentially no environmental impact. The environmental impact comes from training models. And that is happening because, you know, people want to have their online therapists because they want to make funny videos, whatever. That is happening, and I agree. We should definitely think about what we are doing there. But using it is very small impact. Secondly, what I would say is, okay, do you own a car? No. Other people own cars? Maybe students don't. Faculty do, right? I don't own a car. I don't own a car because I think that there's a high environmental impact of that. But people do, and they use their cars because it saves them time, it makes them more productive, all these sorts of things. And we do this in other ways as well, right? Like, you know, we're using the lights here, we're using the computer, right? And so there is a trade that we are making as a society on all of these issues. And I agree there should be a conversation. We shouldn't just go wild. But I would say that in these cases, the impact is relatively small, smaller than driving a car for sure, or having kids. That's your biggest carbon footprint is having children. And so, right, so I think in that sense it's small, still worth thinking about. And then you on the other side you need to say, what do you get out of it? If you just get some meme, you know, all right, that doesn't really add anything. If we learn something about the universe, I would argue that it does add something, and then you have to balance it. Yeah.
More questions?
Becoming vegetarian? I'm pescatarian, very, very good as well.
Yeah, of course, that this is the risk about the utility. We can do it with EA, but what is the risk in the quality of the data?
Yeah, so there are certain opportunities that you just can't do because you don't have enough eyeballs. And so in that sense, like some of the things that we've already been able to do, we just wouldn't have been able to because we don't have enough people looking at the data. So that in that sense, you're gaining. But the place where you want to be very careful about are false positives. And so, early on when we were using machine learning to identify supernovae, one of the closest supernovae in the last several decades was missed by that software because it happened in a very nearby galaxy and it was very bright. And then that algorithm wasn't trained on that kind of model, right? It looked at other supernovae that were very typical. So you have to be very, very careful about these things. And part of what I'm hoping to be able to do is something called active learning, where as you get more classifications, as you say, oh, this was interesting, this wasn't, you're constantly retraining your model, and that just continues to improve things. I will say the models we have now, they're generally better than humans.
Oh.
Yes.
Oh, okay.
Yeah, generally better than humans. Maybe not the experts like Shri or something like that, but the average graduate student, they're pretty comparable with the AI doing a little bit better.
Okay.
And then the students can work on the actual science rather than selecting things and doing all of that.
Okay, thank you. And the other question is, you have all the plan for the development of this project, and you have
It's for the spectrograph.
Yeah.
So we're currently building it. With the University of California Observatories, we are working with the National Astronomical Research Institute of Thailand to build this spectrograph. So we have had a lot of engineering help for people in Thailand to fabricate the instrument. They're getting new equipment for that. They're learning new techniques. It's been a really fruitful partnership. And so we'll get this spectrograph. They'll get some time on our telescope. But what's really great is they have a carbon copy of that telescope in Thailand. And so once we know that spectrograph works, they can just make a second one. Right? Like the plans are there, they know how to build it, so it makes it very economical. So that's been very useful. And the University of California Observatories has been trying more and more to have these sorts of international partnerships for instrumentation, for telescope work. And so, one thing that I think is great here is that people are very good at building instruments, running telescopes. And so I think there's a lot that, could happen between our institutions.
Okay, thank you very much. Yeah.
Of course.
Yes, again.
Put me on the spot.
No. I'm just want to comment that every time that I see the supernova classification plot, I see new families.
Yes.
So could you please tell us something more about how do you distinguish that a new family is appearing? Or First, if just with photometry, spectroscopically?
Yeah, so this is a very complicated issue because there's all this history behind it. So supernovae are, at least classically, they're classified based on their optical spectra. So when you go all the way back to like the 1930s, you're able to separate into type 1, type 2, which was type 1, no hydrogen, type 2, hydrogen. Okay, well, come to the 80s, people realized that some type 1s, they have helium, but they don't look like the normal type 1s. Okay, well then we made a 1A and a 1B. Then we saw, some of them have no helium, but they really look like the ones that have helium except no helium, and they don't look like these other ones. They happen to come from star-forming regions and star-forming galaxies. Call that a type 1c. At that point, things were manageable, but things have just sort of exploded, and people don't use this like type 1 to whatever system anymore. There's calcium-rich transients, which are also called oxygen-poor transients, which are also called CARTs, which is like a bunch of different things. Superluminous supernovae that comes from some actual luminosity cutoff. It's it's kind of the Wild West right now in terms of classification. And part of that is because you want your classification to be observational, because otherwise you would be updating things constantly. But you always, what you really want is the physics. And so you need to be able to connect the observational classification to the physics. And so often people will talk about type 1a supernovae as being white dwarf supernovae, right? And that's true, but some of the other things are a little bit more complicated, where, all right, type 1c, for the longest time, we thought that they were probably coming from Wolf-Rayet stars. Wolf-Rayet stars are massive, they don't have hydrogen and helium, they should explode. But we've never seen a Wolf-Rayet star as a progenitor for a type 1c. But we have seen systems that look like the type 1c's come from binaries. So not a Wolf-Rayet star. So if we would have called those Wolf-Rayet supernovae, we would probably have to update things. So it's complicated, but yeah, the taxonomy is becoming harder and harder, and I feel like you have to have this encyclopedic knowledge of individual things to be like, oh, it's this dash 2 dash, yeah, it's hard. Yeah.
Thank you.
One last question. In Zoom, is there any question? If you have a question in Zoom, please go ahead and open up your mic. Okay, I guess not. So before thanking Ryan, we have some announcements about what's going on tomorrow. So tomorrow, first, we have the Demi Colloquium that is going to be here at what time?
From 9 to noon.
Okay, from 9 to 12. Then we are going to have an extraordinary colloquium on the old auditorium, who will be given by a postdoc who's also visiting. Then at 1, we have a meeting about the young supernova experiment, who's going to happen here. And I think that's all. Then for the students and postdocs who are going to stay for the meeting with Ryan and Shri right now, you just stay here in the room. So that's it. Everyone else can go.